He knows a lot about the science stuff. Professor Dave explains.
Make sure to take the exam before watching this step-by-step answer guide. The link to the exam is in the description. Question number 1 says, in terms of intermolecular forces, which of the following compounds is only capable of London dispersion? So we have different kinds of intermolecular forces possible. There could be molecules that do dipole-dipole interactions, for example, but one of these is only capable of London dispersion. In order to check out what's going on, we want to draw these molecules out so we can identify what kinds of bonds are present. CH3CH2OH, we've got that OH group there. CH3F, we've got that central carbon atom, and then we've got the F, and then we've got some hydrogens. So that's got that tetrahedral geometry. CH2CH2, that means that we have a double bond, because every carbon is going to have 4 bonds there. And then we have HBr. So what do we notice about the types of bonds that are present? In order for something to do dipole-dipole interactions, we have to have some bond dipoles. We need to have some polar bonds there. Can we find some polar bonds? Most of these do have polar bonds. So for example, on ethanol there, we've got an OH bond. This is partial minus, this is partial plus. So that is a polar bond, and that bond dipole is going to be able to interact with other bond dipoles to make dipole-dipole interactions. In this case, they're specifically hydrogen bonds. And then over here, we have a polar CF bond, right? This is also polarized towards the fluorine. The carbon is going to be partially positive. The fluorine is partially negative. The same thing with HBr. We've got a partially positive H, and we've got a partially minus bromine. And so those are examples of polar bonds that are going to be able to make electrostatic interactions with other polar bonds that will be dipole-dipole interactions or hydrogen bonds that are stronger interactions than London dispersion. However, over here, we don't have any of those. With CH2CH2, these are all nonpolar bonds. So carbon-carbon bonds are obviously nonpolar, completely nonpolar. And CH bonds, there's not enough of an electronegativity difference there to consider that a polar bond. So we would say that these are all nonpolar bonds, and therefore it is not able to do any dipole-dipole interactions or anything of that magnitude. We're going to say C right here. That is CH2CH2. That is the only molecule that is only capable of London dispersion. Okay, number 2 asks, which of the following compounds contains a central atom that is sp3d hybridized? So in order to assess this, we need to be able to draw Lewis dot structures. We need to be able to draw these out, ideally with the appropriate geometry. So let's go ahead and do this. We've got, the first one is beryllium. So we have BeH2. So there's our beryllium. And beryllium only has 2 valence electrons. So that is only going to be able to make 2 covalent bonds. That's going to adopt a linear configuration there. B is PCl5. Now, phosphorus has 5 valence electrons, so it is able to make 5 bonds. It can utilize d orbitals and make 5 bonds. So let's put one Cl up there. Let's put a Cl right there. Let's put a Cl right there. And then we've got to show that trigonal planar aspect of the central part of the molecule there. So we've got that situation. This is a trigonal bipyramidal geometry. C is SF6. Sulfur has 6 valence electrons, so that is able to make 6 covalent bonds. So it will make 1 bond to each of these fluorine atoms, and it will do so in a octahedral geometry. So there is SF6. And then we have CCl4. Carbon has 4 valence electrons, so it can make 4 covalent bonds. Therefore, it will have a tetrahedral geometry. Now, in order to generate hybrid atomic orbitals, an atom has to take its atomic orbitals and hybridize them, and every energy level, if we recall, has access to 1 s orbital, 3 p orbitals, and then 5 d orbitals. So all we have to do is figure out how many electron domains are surrounding the central atom, and then we just count up how many atomic orbitals we need to get those hybrid orbitals. So for example, the beryllium atom here, we're looking at 2 electron domains, so that is going to be sp hybridized. We need an s orbital and a p orbital, 1, 2, sp hybridized. CCl4, we've got 4 electron domains, so that's sp3 hybridized. We need an spp, right? We need 4 atomic orbitals there. So that's sp3. SF6, we have 6 electron domains, so we need sppppdd. We need sp3d2 orbitals there. So it really is the phosphorus atom here. We've got 5 electron domains, so we're going to take the s orbital, the 3 p orbitals, and 1 d orbital in that energy level, and we're going to get sp3d hybrid atomic orbitals. So that phosphorus atom there, we would call that sp3 dehybridized. That's going to be PCl5b. 3 asks, which of the following compounds exhibits trigonal pyramidal molecular geometry? So in order to assess this, we need to, first of all, be able to draw accurate Lewis dot structures, and then we need to show the accurate molecular geometry as well. Looking at something like CO2, carbon is the central atom that has 4 valence electrons, so it's going to be able to make 4 bonds. So it is going to make double bonds to each oxygen atom. And so that is going to be the geometry of the CO2 molecule. Then looking at CH4, now carbon is making 4 covalent bonds, 1 to each of the hydrogen atoms. So that is going to show a tetrahedral geometry rather than a linear geometry. There is our CH4. Now BF3, boron has 3 valence electrons, so it can make 3 covalent bonds. So it's going to make 1 covalent bond to each fluorine atom. It's very important to understand that boron has only 3 valence electrons because that affects the geometry of the molecule. With only 3 electron domains surrounding it, it is going to adopt this configuration that we see here, as opposed to ammonia, NH3. Nitrogen has 5 valence electrons. So if it's going to make a covalent bond to each hydrogen atom, that's 3 bonds, that requires 3 valence electrons, it is going to have a lone pair left over. And so what nitrogen is going to do in ammonia, it is going to have this configuration as opposed to the trigonal planar configuration of BF3. Boron is surrounded by 3 electron domains, and the furthest apart that these 3 electron domains can get from one another is by adopting this trigonal planar configuration where they have 120-degree bond angles. That is the farthest away that those 3 groups can be. But with ammonia, we have that 4th electron domain because the nitrogen atom has a lone pair, unlike the boron atom. So that's a 4th electron domain, and that is what forces it to adopt this more tetrahedral-looking configuration, which, if it was CH4, right, CH4 has the same electron domain geometry, but we would call this tetrahedral, whereas with nitrogen, one of those groups is not an atom, but actually just a lone pair. We're going to call that trigonal pyramidal. So ammonia has trigonal pyramidal molecular geometry. Number 4 asks, how many pi bonds are present in the following compound? So what we have to recall is that covalent bonds can be either sigma bonds or pi bonds. And single bonds are sigma bonds. So these are all sigma bonds right here. Now, when you have double bonds, it is the case that one of those bonds is a sigma bond and the other is a pi bond. So here is a double bond right here. This is a sigma bond, and then this is a pi bond. And so the reason this is the case is that when you have 2 carbon atoms that are doubly bound, you have the direct overlap of these orbitals, and that is what produces the sigma bond. And then you have lateral overlap of the unhybridized p orbitals, and that is what produces the pi bond. That is why every double bond consists of 1 sigma bond and 1 pi bond, and that is also why single covalent bonds are sigma bonds, because you first have to have that direct overlap of those orbitals in order for those atoms to be bound to one another, but then you have that lateral overlap of those unhybridized p orbitals that is going to produce another covalent bond between the 2 molecules. Given that every single double bond is 1 sigma bond and 1 pi bond, that means we have 1 pi bond there for that first double bond, and then over here for the carbonyl, again we have a sigma bond between the carbon and the oxygen, and then that second bond is a pi bond. So we have 2 pi bonds total, and so the answer is C2. Okay, number 5 asks, which electron domain geometry exhibits 109.5 degree bond angles? So our options here are trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. So let's draw these out generally, just so we can refresh our memories as to what it is. And let's just put X in the center, and then trigonal planar is going to look like that. Trigonal planar, these are 120-degree bond angles. So that's not it. What about tetrahedral? If we have a central atom there, tetrahedral looks like this, where we have 3 atoms in plane, and then the wedge bond means we're coming out of the screen, and then the dash bond means going into the screen. This is how 4 groups, 4 electron domains, can be as far apart as physically possible. And these are the 109.5 degree bond angles that we're looking for. So that is the answer. But let's check the other 2 just so we can refresh our memories about those as well. Trigonal bipyramidal looks like this. So we have a trigonal pyramid on either side of the central atom. And so we have one going up there, one going up there. And then we have the dash and wedge bonds here. This is a mixture of angles. We have the 120-degree bond angles there, and then we also have 90-degree bond angles there, but none of those are 109.5. And then lastly, octahedral looks like this, where we're essentially setting up an octahedron, and then those are completely 90-degree bond angles. So it's a good idea to remember these different electron domain geometries and the bond angles that are involved. To answer the question, we know that this is going to be B tetrahedral. Okay, number 6 asks, which of the following compounds has the greatest net dipole? So we have CH3Cl, CH2Cl2, CHCl3, and CCl4. So these are very related molecules. Now let's go ahead and draw all of them out just so we can really compare them. First we have CH3Cl. Let's put the Cl there, and then we have our hydrogens. Now we have CH2Cl2. Let's keep all those chlorines in plane and put the hydrogens there. Then we have CHCl3. So again, the central carbon. Now we have 3 chlorines. That remains a hydrogen, and then CCl4. So now we've got all chlorines. In order to assess the greatest net dipole, so it is true that every carbon-chlorine bond is polar. We have polar bonds, and they're all the same type of polar bond. They're carbon-chlorine bonds. But in order to assess the polarity of a molecule, you take all of those individual bond dipoles and you combine them to get the overall net dipole for the molecule. So the geometry of the molecule does matter. For CH3Cl, we have this one bond dipole. So the bond dipole for that CCl bond is essentially the net dipole for the molecule. And then as we add chlorine atoms, we're adding other bond dipoles that will change the configuration of the net dipole. And so for this one here, we've got this bond dipole and we've got that bond dipole. And so to get the overall net dipole, you're essentially doing vector addition. So you're taking these 2 bond dipoles and you're adding them up. And what you end up with is the overall net dipole in green there. But because you're adding these bond dipoles together that are pointing in different directions, you end up getting a smaller net dipole. The length of that vector ends up being smaller than the other bond dipoles. So it actually diminishes the overall polarity of the molecule. And you can say the same thing with the 3 bond dipoles. If we take this, now we have 3 bond dipoles. Now, the net dipole has to point in a direction that is sort of the average of those 3 bond dipoles. So it's kind of hard to draw here. It would essentially be sort of semi coming out of the screen right there. You have to combine all of them, and because they're all pointing in different directions, when you add them up, the bond dipole becomes even smaller than it was for CH2Cl2. And then this culminates in CCl4, which actually these bond dipoles are all pointing in directions such that they perfectly cancel out, and CCl4 ends up having no net dipole at all. So CCl4 has polar bonds, but is nonpolar overall. So we have to go back to the start here, and it is a little bit counterintuitive because you might think if there are more polar bonds, then the molecule should be more polar overall. But it is actually not the case, because as we said, when we start adding CCl bonds that are pointing in different directions, the overall net dipole ends up getting diminished the length of that net dipole is smaller. So the most polar molecule actually ends up being CH3Cl because it is the one that has just that one bond dipole that doesn't end up getting shortened by doing any kind of vector addition. So that one is going to be the answer. A will be the molecule with the greatest net dipole. I've made 12 organic chemistry practice exams to help you ace OChem this semester. Start by taking my free OChem 1 assessment test. Sign up for Community for free today. Number 7 asks, which of the following compounds is the least water soluble? So how do we dictate the water solubility of a compound? Well, we know that water looks like this, and we know that water is a polar molecule. We know that the oxygen is partial minus and the hydrogen atoms are partial plus. And so water is able to do dipole-dipole interactions, and specifically it is also able to do hydrogen bonding because OH bonds are one of those three groups, OH, FH, or NH, that are capable of hydrogen bonding. The compounds that are most water soluble are those that are best able to interact with water and produce favorable electrostatic interactions that bring the system to a lower energy. So we want to look at these compounds and look at what kinds of interactions they're able to make with water molecules. So if we look at CH3OH, methanol has an OH group, just like water has an OH group. That is going to be able to do hydrogen bonding with water. So that's going to be quite nicely water soluble. If we look at ammonia, we have a similar situation. Ammonia also has groups that are capable of hydrogen bonding. Remember that FH, NH, and OH groups are capable of hydrogen bonding. And so this will be able to do hydrogen bonds with water molecules where we have interactions like this, where the partial plus H on water interacts with the partial minus N on ammonia, and the partial plus H on ammonia interacts with the partial minus O on water. Those are potential interactions that will enable ammonia to be highly water soluble. Now we look at acetic acid, and we see that acetic acid also has this OH group. And so this is also going to be able to interact with water molecules in a very similar way. And in fact, it also will do some acid-base reactions. But even the intact acetic acid molecule, this OH group will be able to do these kinds of interactions with water molecules. The only one that can't do any of these things is butane. So butane has all CC and CH nonpolar bonds. There are no polar bonds in the butane molecule, so it has no opportunity to do any kind of dipole-dipole interactions or any kind of favorable electrostatic interactions with water molecules. It will be able to do some weak dispersion interactions, but on the whole, it is not going to be very water soluble because it cannot make favorable interactions with water molecules. And so as we know, nonpolar stuff and polar stuff like water, those tend to be insoluble, and so that one is going to be D. Butane is definitely the least water soluble of these options. Number 8 asks, which of the following elements has its outermost electrons in the 4s subshell? When we're looking at the periodic table, we have to understand that this is the S block, this is the P block, and this is the D block. So all we have to do is look at the specific element in question and see where its valence electrons lie. So, for example, we have calcium. Calcium is right here. So that does sit in the S block. Now, which period is it in? This is period 1. This is 2, 3, 4, and we just go down like that. Calcium is in period 4, and it does sit in the S block, which means that its outermost electrons are 4s electrons. The electron configuration of calcium ends in 4s2. We have an argon shell, and then the last 2 electrons will be sitting in the 4s orbital. So that is actually the answer. It is calcium right there. Let's go through the other options so that we know what's happening with those. So bromine is right here. Now bromine is sitting in the P block, and so its electron configuration involves having 4s electrons and then 3d electrons. So remember that the d is always one behind the s and the p in terms of period. So these are the 4s electrons and then a full 3d subshell. And then it will have 1, 2, 3, 4, 5, 4p electrons. So that will end in 4p5. Magnesium is right here. That is in the s block as well, but it is in period 3. So that will have an electron configuration that has a neon core, and then it will end in 3s2. So its outermost electrons are 3s electrons. Then lastly, we have scandium, which is right here. That has dipped into the d block, and so now we're looking at the outermost electrons being 3d orbitals. But the question asked about having outermost electrons in the 4s subshell, so that certainly is going to be calcium, which ends in 4s2. Number 9 asks, how many resonance structures are possible for the nitrate ion NO3-? So the first thing we have to be able to do is draw the nitrate ion. We have nitrogen right there, and we know that we're going to be surrounded by 3 oxygen atoms. What is going to be the case is that we have to have a double bond to one of them, and then single bonds to the others. And the way this works in terms of formal charge is that we've got minus charges on 2 of the O's and a plus charge on the central nitrogen atom. So the reason for this is that nitrogen has 5 valence electrons, but it is only showing 4 in this particular Lewis structure. 4 is 1 less than 5, 1 fewer negatively charged particles. That is going to have a formal positive charge. And then oxygen has 6 valence electrons, but here it is showing 7 because each of these has 3 lone pairs. So 1 additional negatively charged particle compared to its valence, 7 electrons instead of 6, because we have 3 from the lone pairs and then 1 in that covalent bond that is being provided by the oxygen. Each of those oxygens will have a formal negative charge, and then we have 2 minus charges and 1 plus charge, so that adds up to -1. That is why overall the nitrate ion has a formal negative charge. Now, we want to be able to draw resonance structures for this, and in order to draw resonance structures, we are pushing around pi electrons. Pi electrons are those that are present as lone pairs or in pi bonds. Now remember, in a double bond, one of the bonds is a sigma bond and the other is a pi bond. So wherever you have double bonds, one of those bonds is a pi bond, which means it could potentially be delocalized. And that is the case whenever we're looking at resonance structures. So let's draw some electron pushing arrows here. We can take a minus charge, which represents one of these lone pairs, and we can push that onto this NO bond. So this arrow signifies that we are adding a bond there. We're forming a second bond in between oxygen and nitrogen there. But in order for nitrogen to accommodate that bond, it's going to have to lose another bond. So let's push that pi bond onto that oxygen atom. That will end up looking like this. We have produced a new double bond there. Nothing happened on that one there. And then here we now have just a single bond to oxygen with a minus charge because that pi bond ended up on the oxygen, so that oxygen gained an electron. Now we can do the same thing over here with that third oxygen. Let's go ahead and push that there and then push this up onto that oxygen. That ends up giving us this. Now we've run out of possible resonance structures. And let's go ahead and put the plus charge on the nitrogen in both cases. The 3 possible resonance structures, again, we have nitrogen bound to 3 oxygen atoms, and we need a double bond to one of those oxygens, but it could be any of the 3 oxygens. We end up with one resonance structure with a double bond to that oxygen, another resonance structure with a double bond to that oxygen, and then a third resonance structure with a double bond to that oxygen. Those are the 3 possible resonance structures, so the answer is C. 3. Number 10 asks, when 2 atomic orbitals overlap, how many molecular orbitals will be produced? And we have 1, 2, 3, or 4. So let's look at the simplest situation possible. If we're going to make a molecule of H2, we have a hydrogen atom with its 1s orbital, and then we have another hydrogen atom with its 1s orbital. And what we're going to end up getting is we're going to end up getting a bonding molecular orbital, 1s molecular orbital, and we're going to get an anti-bonding 1s star orbital. What we understand here is that anytime you are taking atomic orbitals to produce other kinds of orbitals, whether they are hybrid atomic orbitals or molecular orbitals, there will always be a conservation of orbital number. So we're taking 2 atomic orbitals and we're producing 2 molecular orbitals. As it happens, the electrons are going to be sitting in the bonding molecular orbital to produce the H2 molecule. So those are both in there. right? We have a 1s electron there, we have a 1s electron there. They're both going to end up in the bonding 1s molecular orbital, but we are also producing an uninhabited anti-bonding 1s star orbital. And so the answer here is just testing if we know how many molecular orbitals are being produced, namely a bonding and an anti-bonding orbital as a result of the interaction between the atomic orbitals. So the answer is B, 2. 11 asks, which of the following compounds is capable of hydrogen bonding? Now remember, hydrogen bonding is a certain type of dipole-dipole interaction that can occur between FH, OH, and NH bonds. So a molecule that can hydrogen bond must have one of those groups present in it. Now here we have everything in this sort of condensed formula notation, so I think it is going to be best if we can draw these out so we can really see the exact connectivity between the central atom and everything that's going on. So let's take that first one. We have a central nitrogen atom, and then the nitrogen is going to have 3 groups. So we have an H, and then we have 2 methyl groups. Now, B is NCH3. It's a trimethylamine, so we have all methyl groups. All of the 3 groups around the nitrogen are methyls. Then we have CH3COCH3. This can be a little tricky when we go from the condensed formula to the line notation because CO seems a little ambiguous. But when we have a situation like that, we have a carbonyl. So that is acetone. And then D says CH3COOCH3. So this also can be a little confusing, but when we have that situation, we know that we have an ester. So CH3 is the methyl there, and then CO is the carbonyl, and then another O is that other ester oxygen before another methyl group. So remember, for hydrogen bonding, we need FH, OH, or NH bonds. One of those groups need to be present in order for hydrogen bonding to be possible. Where do we have such a group? That is right here. This is the only compound that has one of those groups. We have a nitrogen bonded to a hydrogen atom. That's an NH group that qualifies for being capable of hydrogen bonding. These ones do not. They all have NC or CO or CC or these other types of bonds that do not qualify. So the answer is going to be A, this molecule there. And then going back to these 2 molecules, let's just make sure it's very clear what these represent. So these are methyls at the end there. This is a methyl right here. This is a methyl right here. And when we're talking about these groups, these are called functional groups. So this is a carbonyl. This particular carbonyl is present in a functional group called a ketone. That's when we have a C double bond O with more carbon material on either side. This is something called an ester when we have C double bond O and then another oxygen and then alkyl beyond that. And so we're going to learn a lot more about these as we proceed through organic chemistry. These functional groups are very important in terms of understanding how a molecule behaves, how it reacts. So stay tuned for more of that. Number 12 asks, which noble gas exhibits the weakest dispersion forces? So with the noble gases, we're talking about monoatomic species, so they certainly cannot do any kind of dipole-dipole interaction, ion-dipole, ion-ion, any of these other things, because there are no covalent bonds, right? Dipole-dipole interactions require a minimum of 1 bond dipole to be present, so you need covalent bonds. These do not have covalent bonds. These are all monoatomic species. Now, what is the difference between these species? As you go down the periodic table, here is helium, neon, argon, krypton, and as we go down the table, we're increasing in size. Because every time we go down one period, we're adding an additional shell of electrons. So we have period 1, period 2 has that second shell of electrons, 3 has the third shell, 4 has a fourth shell. So what we're talking about is we're saying helium is very tiny, neon is bigger, argon is bigger still, and then krypton is much, much bigger still. As we get larger, what does that do in terms of the strength of the dispersion forces that are possible? Well, remember that in order for dispersion to occur, we need a momentary dipole to exist, an instantaneous dipole where the electron cloud is just momentarily polarized one way or another, and then that is able to create an induced dipole in another atom. The larger that the electron cloud is, the greater that momentary dipole is able to be, because the larger it is, the more diffuse it is, the greater ability it has to shift. and shift in one direction or the other with respect to the nucleus. So a larger atom is able to create larger instantaneous and induced dipoles, so those will be stronger dispersion interactions between them. So the weakest of them all is definitely going to be helium, because that is the smallest atom, and so that is the answer for this one. 13 asks, which compound has polar bonds but is nonpolar overall? In order to do this, we definitely have to be able to understand the geometry of the molecule, because in order for something to have polar bonds but be nonpolar overall, that means that the bond dipoles are canceling out in a very specific way. So let's draw all of these with accurate molecular geometry. First, we have ammonia. So we have NH3. Then B is CH2Cl2. That is going to be tetrahedral. C is CH4. And then D is CO2. So that one is going to be linear, because we have two groups. Whenever you have two electron domains surrounding a central atom, that will be sp hybridized and therefore linear. So the question asks, which compound has polar bonds but is nonpolar overall? Well, the first one we can get rid of is methane, because that does not even have polar bonds, right? So if there are no polar bonds at all, the molecule cannot be polar. The rest of these molecules do have polar bonds, but which one of them would be nonpolar overall? So here for ammonia, we have 3 polar NH bonds, and they're all pointing sort of downwards with respect to the nitrogen atom, and so we do end up with a dipole there. We have a dipole where there's an end of the molecule with the partial positive hydrogens, and there's an end of the molecule with the partially negative nitrogen and its lone pair. Then if we look at CH2Cl2, we have a similar situation where we have 2 bond dipoles. So there is a net dipole. When we combine them, we do get a net dipole. It is slightly diminished because of the adding of the 2 vectors, but the 2 vectors are pointing somewhat in the same direction. So we can combine them. We can get an overall net dipole. So we do have a polar molecule overall. But if we get to CO2, we have a polar CO double bond. We have a polar CO double bond going the other way, but because they are precisely opposite in direction, they are equal in magnitude and opposite in direction, this is going to be nonpolar overall. The only way for this to have been polar is that the bond dipoles could be not of the same magnitude. So for example, if we replaced one of these oxygen atoms with a sulfur atom, then we would retain some overall dipole because the magnitudes would be different. We would have one bond dipole being longer and stronger than the other one, so it would retain some polarity overall. But these are exactly the same. It's C double bond O and C double bond O. If they were pointing in different directions, then we could retain a net dipole just like CH2Cl2. But because they are of the same magnitude and in precisely opposite directions, they cancel out completely. So CO2 is an example of a molecule that has polar bonds but is nonpolar overall. 14 asks, direct overlap of atomic orbitals results in blank covalent bonds, and lateral overlap of atomic orbitals results in blank covalent bonds. So we're looking at different kinds of orbital overlap and the different kinds of covalent bonds that they produce. And so we want to go back to our classic example. If we have 2 carbon atoms that are interacting with one another, we can have direct overlap of orbitals that are connecting those 2 carbon atoms, and that is going to produce a sigma bond. And then in order to get further covalent bonds, we have to look at these unhybridized p orbitals, and it is going to be lateral overlap of those that is going to produce pi bonds. What we're saying here is direct overlap of atomic orbitals results in sigma bonds. That's what we are seeing right here. And then lateral overlap of atomic orbitals results in these pi covalent bonds. So which of the options has the correct configuration? A says sigma pi, so that is going to be the one right there. 15. In which solvent will NaCl be the most soluble? So if we want to assess the solubility of NaCl in different solvents, we want to understand the types of interactions that are going to take place in solution. So if NaCl dissolves and dissociates in solution, what we have is we have Na plus cations and we have Cl minus anions. So what kinds of interactions would be possible between these solute particles and the surrounding solvents? Well, we have ions here. These are formally charged particles. So the best situation would be one in which these can make ion-dipole interactions with the solvent molecules. If we have CHCl3, what could that do? If we have H2O, what could that do? And then we have these longer molecules. We have one completely nonpolar hydrocarbon, and then we have an ether here where we have CH3, CH2O, CH2, CH3. So what are the types of interactions that could occur? Again, the best thing that could happen is if we have ion-dipole interactions. The solvent that is the most polar is going to be the one that can generate the strongest ion-dipole interactions. So in this case, it's certainly going to be water. We have partial minus and partial plus. And so what can end up happening is that we can have water molecules oriented like this all around a sodium cation, whereby if this is fully solvated, it is going to be making many interactions. The Na plus is going to be interacting with the partial minus of every water molecule. And then the same can be said for the chloride ions, except for it is going to be with the opposite end of the molecule. We will have all of these interactions between the Cl minus and the partial plus of the hydrogen. This is the case with water, and we're not going to be able to do that with any of these other solvents. With something like CHCl3, this has a pretty weak net dipole. Because of the 3 chlorine atoms here, these bonds are all pointing in different directions, so the net dipole is pretty weak. There is still going to be some interaction, but it is certainly not going to be as strong as with water. Then with the hydrocarbon, this just has no polar bonds. So there's no opportunity for any dipole-dipole interactions, ion-dipole interactions. There is no dipole present with which to interact with formally charged particles. And then the same thing for this ether here. There are polar CO bonds, so there is something there, but they end up even somewhat canceling out. If you look here, we can draw it out completely. We have CH3, CH2, and there's our O, and then a CH2. And a CH3. So these bonds are polar, but they are largely in opposite directions. So we end up with quite a weak dipole overall. Again, there will be some interaction, but the best situation possible is for Na plus and Cl minus to be interacting with the dipole from the water molecules. That is going to be our ion-dipole interactions, and that is why NaCl is so water-soluble. So that one is going to be B, water. If you need a refresher on general chemistry, I recommend watching Community's General Chemistry Review for Organic Chemistry video. This review will help prepare you for what you'll encounter in OChem. Find me on Community, the best online resource to help you ace OChem this semester.